All right, we're going to put a name to some of the field extensions we've seen. So the new term here is a simple extension. So what is a simple extension? Well, it's the simplest type of non-trivial extension. A trivial extension, of course, being something like Q is a subset of Q, where a field is a subset of itself. So a simple extension is a field extension L over K such that L is obtained from K by adding in one and only one number. And necessarily that number needs to be an L. All right. So examples. Well, we saw a bunch already. Q adjoin root 2 over Q is a simple extension. Q adjoin I over Q is a simple extension. R adjoin I over R is a simple extension. Q adjoin the real cube root of 2 over Q is a simple extension. Let's see, Q adjoin pi over Q is a simple extension because we just add in a single thing. We add in pi, and so on. So a lot of the ones that we've seen are simple extensions. Okay, great. Now, caution. Let's look at this extension that we've been dealing with in this chapter, Q adjoin I and root 2 over Q. Now you might look at that and you might say, hey, that's not simple. You add in 2 numbers to Q. 2 is not 1, at least not in a world that I want to live in. So this can't possibly be simple because we add in 2 things. However, what this is saying, this definition is not saying, hey, how it's presented must be simple. It's saying that you can find an alpha such that when you just add in that one alpha, you get the whole extension. So although the presentation is not simple, it might still be simple. Doesn't mean it isn't. The only way to prove an extension is not simple is to rule out that it cannot be generated by any element of L over K. Now, we work in characteristic 0, we work in subfields of C, so that's an infinite number of elements we have to rule out. So that's a lot. So let's observe something for this example here. Let's look at the element I plus root 2. That is certainly in Q adjoin I root 2 because Q adjoin I root 2 has I and it has root 2, so it has I plus root 2. And let's call that element alpha. So let's set alpha to be that. Then let's look at alpha squared. Alpha squared is I plus root 2 squared. And if you square that out, you get I squared plus twice the first times the second plus the second squared. So that's -1 plus 2I root 2 plus 2. So alpha squared is -1 plus 2 is 1 plus 2I root 2. All right, fine. So here we have alpha. Here we have alpha squared. Let's look at alpha cubed now. So that's alpha times alpha squared. Alpha is I plus root 2. Alpha squared is 1 plus 2I root 2. Also notice alpha squared is certainly also in Q adjoin I root 2. That's there. Actually, I don't need to notice that yet. I'm going to do something separately later. Sorry. Let's do this product. All right. So we have first, outside, inside, last. So our first terms are I times 1 is I. Our outside terms are I times 2I root 2. So that's 2I squared. So that's -2 root 2. Oops. And then the insides, root 2 times 1 is positive root 2. And then the last, root 2 times 2I root 2 is going to be a 4I because we get the root 2 squared is 2. So an extra 2 pops out. So we have 5I minus root 2. Cool. So alpha cubed is here. Now, alpha is I plus root 2. Alpha cubed is 5I minus root 2. So what happens, let's see, what happens if we do alpha cubed plus alpha? Oops. Alpha cubed plus alpha. Well, alpha cubed is 5I minus root 2. Alpha is I plus root 2. I believe the root 2's cancel. That gives us 6I, or said differently, alpha cubed plus alpha over 6 is I. Great. Now what happens if we do alpha minus alpha cubed plus alpha over 6? Well, alpha is I plus root 2. This is I, so we're subtracting off I, we get root 2. What this is saying is, if we have access to Q, excuse me, and alpha, then we get I and root 2. We get those for free. Well, not for free. We had to do some work to show that we get them, but they're automatically included in our set. So really, to get access to I and root 2, in addition to Q, we just need Q and a single element, just alpha. And that alpha was I plus root 2. So this extension is actually simple. Although it was not presented as such, that's okay. The extension itself was simple. It's just equal to this extension I plus root 2 over Q. Is simple. We're actually going to prove a fact later on called the theorem of the primitive element, which is essentially going to say any extension like this, we'll call these finite extensions, where you sort of add in, you don't add in something like pi, you add in like a root of a polynomial. Any finite extension is simple. So basically all the extensions that we're going to encounter are simple. They're going to be obtained by taking a base field and adding in a single element to the base field. Okay? So this might seem silly, this idea of defining these extensions where you just add in one thing, one number, but it's actually very useful, and almost all the extensions we're going to look at in this class will in fact be simple.